Thanks for being here at the University of Illinois. So today I'd like to discuss modulus measurements. And first I want to introduce the PhD student that's working on this, Abdul Qadir Idris. Want to stand up real quick? Chuck Oden, who I'm going to talk about a little bit later, Carl Ho, Hugh Thompson, and Ted Sussman. Okay, track ballast / modulus. So here's the European approach. You set a track cross section and you assign different moduli values to the section. And those moduli values are selected for reasons to generate a certain performance. And I think I got this slide from Jerry Rose. So Jerry, thank you. So that's the idea. How can we assess the modulus and build a system around the modulus? Because once we have the modulus, that can help us control the deformations of the system. So modulus can vary across the track, as you see in this diagram, and there can be stiffer parts, weaker parts, and so on. And so that controls the load distribution around the track. And of course, if we then have some degradation of the ballast, that also reduces the modulus and increases the deformations. So how do we measure modulus? It's difficult. Some current techniques, invasive techniques, and you heard about ballast sampling and testing. Some trying to correlate the cone penetrometer, ground penetrating radar, inverse analysis using numerical models, and I'll talk about that in a little bit. And so a while ago, we started with surface waves. Okay, so what are surface waves? When you create a vibration, we create three types of waves: shear, compression, and Rayleigh or surface waves. So we're going to focus on these surface or Rayleigh waves. And so imagine in the bottom diagram right here, throw a rock into a pond or a body of water. Those waves that radiate outward are the surface waves, and that's what we are going to measure. So with those surface waves, we can estimate the shear wave velocity profile. And so this is a measure of shear wave velocity at different depths, and this happens to be a jagged profile, but all I want to do is show you shear wave velocity versus depth, and that's what we'll be measuring with these surface waves. The important part of the shear wave velocity is, notice VS, shear wave velocity, is right here. And I know showing an equation on the second day of a conference, is that terrible? And it's squared. Shear wave velocity is squared. We multiply by the density of the material, and that gives us the shear modulus of the material. And then we just use Poisson's ratio right here, and I'll give you some typical values for fouled sites and clean sites in just a minute for Poisson's ratio. We multiply G by this little expression and we get our Young's modulus. And that's what you saw on the first cross section of the track with different E or Young's modulus values. So that's what we're after, is this E or Young's modulus value through the shear wave velocity. Well, we started this a while ago. There's a photograph from 2013. And so we just had accelerometers at different locations on the track, and we excited it with a hammer or a kettle ball, if you're familiar with that at the gym, just dropping it and creating our surface wave. We next migrated to this little device. It's actually for pavements. We're trying to modify it for rail applications, but it really didn't have enough energy source to excite enough of the track for our situation. So that led to the current project, which is being conducted by ESS, Earth Science Systems, with Chuck Oden. And this is the device that he has created under an SBIR project with the FRA. So here we are at one of the long-term instrumentation sites. Radim in his presentation mentioned the ballast waver project. As part of that project, we had 6 long-term instrumentation sites. I'll show you 2. One is at the control site, which is a clean ballast site, and the other is at a foul ballast site. So you get to see the difference in modulus between the two. But so Chuck has it out. And these are the sensors are sort of GPS connected. So we get the measurements or the distance from the excitation source, which is right here, automatically, and that gives us the distance, and we know the time it takes for the wave to get to each one of those sensors. So we were able to calculate shear wave velocity at each of those points. The farther away the sensor out here, the deeper the signal goes. You can see the excitation source at this point has some weights on it. You can stand on it, as Chuck is doing right here, instead of putting weights on it. But if you want to do something else, you can put the weights on it, run the test. Okay, so that's the C-bit device. And so I think at this point, the hardware is in a good state. So now the question is, what do we do with the data, and how do we take this shear wave velocity profile and convert it into a useful modulus value for track assessment? And so that's the main part of my presentation, SciBit verification. So this is one of the long-term instrumentation sites. There's our instrumentation box, some solar panels to run it, a rain gauge, and some other equipment. Inside the box there, and I'll just focus on the equipment that I'm focusing on today, 2 high-speed cameras watching targets on the track, both the rail and the ties, and that's going to give us the transient displacements of the rail and the ties, and we're going to use that in our calculation of field modulus in just a minute. Also, with the instrumentation site are some rail strain gauges, as you see here. They're placed on the rail, one circuit inside the crib and another circuit over a tie. And so that now enables us to estimate the amount of load going into the tie by subtracting the crib and the distributed load, which comes off this circuit. Here's there's a close-up of the strain gauges on the rail. So now we've got wheel load over the tie, and we have the transient displacement of the tie, which I'm going to use to calculate modulus. So here's Chuck. This is the fouled site. Yeah, this is the fouled site. If you look back here, you can see some fouling material in the track. And here's the associated shear wave velocity profile for this particular site. So Chuck ran this at both the fouled and the control site. So here is the, looks like the control site. So, and you can tell the control site's a little more well behaved. Notice the normalized displacement, which I'm going to talk about in just a minute, versus the applied wheel load graph. All the data seems to lie close to a Young's modulus of about 18.2 megapascals. And just wait, you're going to see the fouled site, and it's going to be a big mess. So the applied stress comes off the rail strain gauges, and this normalized displacement, here's the tie displacement coming off the cameras, and D is the depth of influence of the load into the track. Because strain is the change or deformation divided by the initial height, or the initial height of the specimen. So we estimated that initial height to be about 8 inches. So the zone of influence of the loading of a car going across 8 inches, we looked at that numerically. So today, I don't have time to show you that analysis, but we're going to use 8 inches as D. So our normalized displacement, transient displacement, delta tie divided by 8 inches is what's plotted on the horizontal axis. So here's the control site. There's the fouled site. Each one of those dots is a different train going across the site. So of course you can see much wider variability in the modulus at the fouled site due to differences in, say, the moisture content of the fouling material, among other things. The load is about the same. Notice here's about 0.4, and that's megapascals. And if I go to the fouled site, here's 0.4. So roughly about the same loading, but a much different modulus response out of the fouled site. Okay, I talked about the applied stress, and I've talked about the transient tie displacement and the depth of influence. So then we had to take the wheel load and convert it into an applied stress to estimate the modulus. The applied stress, we used the tie load that I mentioned and the rail contact area at that particular tie. And I welcome any suggestions for improving this analysis at the end, but this is where we're at. So the applied stress is the wheel load divided by the rail contact area, and there's the dimensions that we used. I already mentioned this pseudo-axial strain and using the cameras and our depth of influence of 8 inches. The important thing is these normalized display strains were only about 1 to 2%. And that, I think that's a good way moving forward, looking at how the system's performing in terms of a strain measurement instead of, say, a displacement. Okay, so this is important because we're going to have to use what's called a modulus reduction relationship. I know you, geez, what the heck is that? So when we run a surface wave measurement, these surface waves are going through the ballast and the track system, but it's a very small excitation, very small. So we are measuring a very small strain, shear wave velocity, and shear modulus, okay? Of course, when a train goes past, we are not in the very small strain category. You see the track moving quite a bit. And so we have to use a modulus reduction system or relationship to convert our shear wave measurements, shear wave velocities, to a larger shear strain. So that's what's next. And that's why I converted this tie displacement to an axial strain, because the modulus degradation relationships are based on strain. So here they are. On the left is the fouled site modulus reduction relationships. On the right are the control site or clean ballast site. So that's more like a gravel. So if you are familiar with modulus reduction curves, you'll probably recognize some of these as modulus reduction curves for gravel or large rock. So those are readily available in the literature, and that's great. That helps us a lot. So the curve in red right here is the curve I'm going to use to reduce the shear wave velocity, the maximum shear wave velocity, to a larger strain shear wave velocity. Now, the challenging part is the fouled site, because not only do we have a clayey type material, because the fouling at this particular ballast waiver site was very seriously fouled, and the fouling material consists of a high plasticity clay, not low plasticity. So this is a very active clayey fouling material. So first we have the modulus reduction due to the strain level, but then because the material was basically saturated, we generate pore water pressures as the train goes across the site. So the longer the train, the more the pore pressures develop. And so we have to incorporate that softening due to pore pressure generation into the modulus estimate. So that's another presentation, but I'll speed it up and say this red line right there is the modulus reduction curve that we used for the fouled site, and it includes a pore pressure reduction factor to it. So there you go. There's fouled site. And on the clean or the control site, we did not have to incorporate the effect of pore water pressures. Okay. So here's the comparison. On the left here, this is the modulus of elasticity, the maximum value. So that's using the maximum shear wave velocity. Then if I use 1% strain and the modulus reduction curve, you can see it drops from about a $1.26 to about 12.7. So you'll see in just a minute, some future work is working on these modulus reduction relationships and seeing if we can dial those in a little better and make more consistent predictions of the modulus. But so here's the modulus at 12.7 MPa at 1% strain for the control site, and notice the fouled site is about 9.1 megapascals at 1% strain. The instrumentation that was installed at those two sites, the control site yield about 18.2 and the fouled site about 9.5 using the normalized axial strain that I mentioned. So we're certainly in the right ballpark. There's some uncertainty in the modulus reduction relationships and estimating our axial strain for a particular site and loading, but I think we're getting pretty close. I think the hardware is in place, and now we just need a little work on the analysis side. So summary, seismic surface waves can be used to measure substructure modulus. Possible applications are varying support conditions, so we could see and measure varying support across the track, fouling, and of course, a future aspect is using this to assess tie integrity, because these surface waves go through the ties. So we can look at the consistency of the tie as the wave goes through it, because we have those accelerometers or geophones at different points along the track, and we know if the wave is being slowed down or it's going quickly through the ties as it's going down the track. Future testing, varying degrees of fouling, both dry and wet, change support conditions with time, effective ballast density, and most importantly, these modulus reduction relationships that we use to convert the small strain shear wave velocity measurements to a larger strain to reflect how much movement we're getting on the track due to a passing loaded train versus an empty train. So acknowledgements, of course, the FRA and Hugh Thompson for supporting the research, Ted Sussman of the Volpe Center, of course, BNSF, who hosted the ballast waiver project, and Radim Bruzek was the director of that project. So sorry, Radim, I guess I should have ENSCO on there, sorry. And ISI, Instrumentation Services out of Denver, who helped us put all the instrumentation out on the 6 sites. So I welcome questions, comments about our analysis of measuring and calculating moduli. Yes, sir. Question is, have we tried this at a site where we have a known ballast pocket? Not that I know of. Not that I know of. We obviously 4 sites that we know we have a foul pocket. Cam, please.
Do you have any estimate of the sensitivity of the result to the accuracy of the shear wave velocity? And the second part of the question is, how sensitive is that shear wave velocity?
Right. So the first question is, how sensitive is the calculation to the measured shear wave velocity? Actually, even though it's squared to get the shear modulus, it really isn't that big of a deal. It's a small number. I think the bigger uncertainty is in the modulus reduction curves. So if you look at the modulus reduction curves, so you can go, so this is what we're measuring at G max. So notice the graph is G over G max. So G over G max is 1, and that's where we measure the shear wave velocity. You can see the strain very, very small. I mean, you know, you don't see the track moving when you run a shear wave velocity test. Anyways, so, but notice the modulus reduction takes it from 1 down to 0.1. So there's a 90% reduction in the measured shear modulus. Okay, Cam, the second question is, does the amount of energy applied to the test affect the shear wave velocity? No, and the excitation source that Chuck developed, there's like 8 different settings of energy into it. So it cycles through all levels of energy. It's once you hit it, you'll hear it go, it'll run through the whole cycle of loading. And did you see the shear wave velocity profile at the Hickman site? Oh, there it is. So there's some different lines underneath here, but basically they all fall in a pretty tight band, even with different levels of energy. Other questions? MD.
You assumed 8 inches under your control site of load distribution. Did you assume that same value for the fouled site? And is that appropriate given the fouling is going to have a completely different state?
Okay, first, MD, I want to correct, didn't assume. So we ran some LS Dyna numerical analyses to look at the depth of influence of under the applied loads that we had measured at the site. So that the analysis shows us about 8 inches. And that's closer to the control site than the fouled site for sure. But still about roughly the same. I mean, and the reason that's important is in the beginning, we were using the full thickness of ballast to divide the transient displacements by. And make that long story short, that lowered the strains so much that I didn't think they were reasonable. So that's why we went to the analysis. So I don't think it's just using the full thickness of the ballast. Any other questions? Okay, great. Thank you very much.